Okay, welcome back. We had established some a priori estimates for the flow of convex hypersurfaces by mean curvature flow, and it remains to show that these estimates imply convergence to the round sphere. So let's call this convergence to round points of convex curvature flow. And so the situation was we had a mapping from, in this case, it's an Sn cross some maximal time interval. You had already seen this has to be finite into Rn plus 1 with the standard metric, and solving ddt f equals mean curvature vector. And we had assumed that the initial surface is convex, meaning that it immediately becomes uniformly convex. So without loss of generality, we can assume that each principal curvature initially is bigger than some fixed multiple epsilon of the mean curvature, and the mean curvature is positive. And then we had shown with the maximum principle that this epsilon is preserved as a fixed parameter for all time where the solution exists. And then we had established the two crucial a priori estimates that showed that the surface becomes better during the evolution. First of all, we had shown that the trace-free part of the second fundamental form, so this is the full norm squared minus 1 on n h squared, satisfies a pinching estimate. We had some C0 times h to a power slightly less than 2, meaning that the scaling invariant part of the trace-free part of the second fundamental form converges to 0 if the mean curvature goes to infinity. And then secondly, we had used this estimate to get a gradient estimate on the mean curvature. We showed that for any eta, we can find a C eta such that the gradient can be estimated. And let's write this, let me write this for the next step. And in this form, I think I formulated it first with just an eta here, but of course, eta can be anything. You can take eta squared. And, and this says, of course, that the scaling invariance is sort of mildly broken because eta can be chosen as small as we want, and the C eta is scaling much less than the h squared if h goes to infinity. So the next step, the next step is to show that not just if the mean curvature blows up somewhere, and therefore at some point we have sort of the thing look like a sphere at the curvature level, but if it blows up somewhere, it blows up everywhere. So the proposition says that the ratio of the minimum and the maximum of the mean curvature at time t converges to 1 as t approaches the maximum time. This is the next step we want to show. And we use the gradient estimate for that. And the idea is to use the convexity to show that if the mean curvature is huge somewhere, then because of the positive Ricci curvature that follows from the convexity, we get conjugate points along any two geodesics, meaning that the manifold has to close up in finite distance. And the tool for this is Meyer's theorem. Let's recall Meyer's theorem if on a Riemannian manifold mng n greater or equal than 2, we have a lower bound on the Ritchie curvature. Each eigenvalue of the Ritchie curvature is bigger than n minus 1 times some number k times the identity matrix, meaning each eigenvalue of Ritchie is bigger than n minus 1 times k, then any geodesic gamma of length L of gamma greater or equal than pi times k to the minus 1/2. This is exactly the distance on a sphere of curvature k from the North Pole to the South Pole. So any such geodesic has conjugate points, has a conjugate point. Conjugate points always need 2 points to be conjugate to each other. Right? And this is proved with a second variation argument along geodesics. And with this, we can prove the proposition. So proof proposition. First of all, notice that since H max tends to infinity as t tends to t max, we can make this c eta close to t max smaller, much smaller than eta squared times h max squared. For any eta that exists at theta less than t max, such that gradient h is less than 2 eta squared h max squared at t theta. So the second term in the inequality for the gradient of the mean curvature becomes irrelevant at points close at times close to the final time with respect to the maximum curvature which goes to infinity. So if we then take a point P naught is a point on the surface at time theta such that the mean curvature at that point attains its maximum, and gamma is any geodesic emanating from P naught at time t equals theta. So we take the Riemannian metric now at the induced metric at time theta. Then along gamma, we can estimate that the mean curvature at gamma of s the mean curvature at the start point, which is h max at theta, drops off to the mean curvature at gamma of s of theta by at most this difference can be estimated by the fundamental theorem of calculus. So we get the gradient of h along this curve. And now we insert our estimate here, so this is less than 2 eta squared h max squared at theta times the length of the curve. And so if we now choose the length of the curve, is less than 1/2 eta to the minus 1 times h max to the minus 1 at theta. Notice that this scales right, h max to the minus 1 scales like a length and has a huge factor because eta is going to go small. So this is a huge factor times the appropriate scale that we are at. So this is a long distance. Then along this curve, the term on the right-hand side has still an eta in front of it. So we get that h along the curve is bigger than 1 minus eta times h max. But despite the curve being very long, it remains very close to the maximum of theta. Now we want to apply the Meyer's theorem, so we need to look at the Ricci curvature. But for the Ricci curvature, we use our convexity. So let's look at the Ricci tensor. By the Gauss equations, the Ricci tensor is given by the mean curvature times the second fundamental form minus the square of the second fundamental form, which means that each principal curvature, each eigenvalue of the Ricci tensor, when Hij is diagonalized, we get the matrix here H times lambda 1 minus lambda 1 squared, and we get H lambda 2 minus lambda 2 squared, and so on up to H lambda n minus lambda n squared. But we can take the eigenvalue out. So this is lambda 1 times h times lambda 2 plus lambda n and so on. And then we get lambda 2 times lambda 1 plus lambda 3 plus lambda n and so on. So we see that in each term, we can apply our convexity estimates. So we get that Rij, since each lambda I is bigger than epsilon times h, this must be bigger than epsilon squared times n minus 1 times h squared. Because we just apply the convexity estimate to each of these eigenvalues. So we get this times Gij. But this h squared, on the other hand, along the geodesic, we have just seen is bigger than epsilon squared 1 minus eta squared times n minus 1 times h max of theta squared times Gij. So the k here for Meyer's theorem, the k is equal to epsilon squared 1 minus eta squared times h max squared. So if we apply Meyer's theorem, we see that this geodesic, so gamma has a conjugate point. If the length of gamma is greater or equal than pi times k to the minus 1/2. So this is pi times epsilon to the minus 1 times 1 minus eta to the minus 1 times h max to the minus 1. On the other hand, we saw that our estimate is true as long as L of gamma is less than 1/2 eta to the minus 1 times h max to the minus 1 theta. And now you see that both these inequalities can be easily fulfilled, since this one here is always bigger than eta close to 1/2. So this is close to 1. So this is also close to 1. So this is just a fixed constant depending on epsilon and pi. So we can easily satisfy both this inequality and that inequality if we choose eta small enough. It's both possible for eta less than some eta naught, which just depends on pi and epsilon. But then all these geodesics going in any direction have conjugate points. But that must mean that in particular the geodesic that goes from the maximum point of the mean curvature to the minimum point of the mean curvature must be satisfying these inequalities if eta is small enough. And therefore we get an estimate on the diameter of the manifold, and we get at the same time that the minimum has to also satisfy, the minimum of h also has to satisfy our inequality. So as a consequence, so these geodesics also reach all points of the manifold, all points of the manifold, in particular the point where the minimum of the mean curvature is attained. Therefore we get that the minimum of the mean curvature is bigger than 1 minus eta times h max. And we even get more. This of course implies that the minimum over the maximum tends to 1 as eta tends to 0, and then which means that theta tends to T max. And in addition, we get a corollary that the diameter m and theta is less than a constant divided by h max at theta for theta bigger than some theta 0 less than T max. Okay. So we can relate the diameter of the manifold to the maximum because of this estimate here. We can do this for a fixed eta naught, and therefore all these geodesics satisfy this estimate, and they have conjugate points, so they also realize the furthest point. Okay. Now, with that, we have the right scale. Now, we want to show that this also implies a precise scale in terms of remaining time for the blow-up rate of the curvature. So the next proposition, blow-up rate curvature, can be shown, we can show that for theta close to T max, we get that there exists a C3 less than infinity such that the mean curvature is bounded by the square root of the remaining time. And the denominator, and similarly in the other direction, C3 to the minus 1 divided by square root of the remaining time, which is of course exactly the blow-up rate of the sphere and the cylinder. So this proposition says that in the convex case, we have exactly the same blow-up rate as the sphere has and as the cylinder has. And the proof, we can use the comparison principle to get a lower bound on the maximum of the mean curvature. So consider the evolution equation of h. This is the Laplacian of h plus h times the square of the second fundamental form. And in the convex case, this is of course less than h cubed. This means that in the sense of lim sup of difference quotients, the derivative of h max, the maximum, the Laplacian is less or equal to 0. So we can estimate this by h max cubed. Sort of an ODE in the sense of difference quotients. And of course, we can also write this as ddt of h max squared is less than 2 times h max to the 4, which in turn implies that ddt of the inverse is greater or equal than minus 2 times h max to the minus 4 multiplied with h max to the plus 4. So we get a minus 2. And then integrating this from, so for t1 bigger than t, we get that h max minus 2 at t1 minus h max to the minus 2 at t must be bigger than minus 2 times t1 minus t. And if we now let t1 tend to t max, then this goes to 0. Because we know that t max, that at t max, the maximum of the mean curvature goes to infinity. So we get from here a bound on h max to the minus 2 from above, which gives us a bound on h max of t from below by 1 over 2 times the remaining time. So we know that the maximum has to blow up at least at this rate. Cannot blow up at the lower rate just by a simple comparison with the ODE. On the other hand, we know that the minimum is at least a fraction of the maximum, since the ratio between minimum and maximum tends to 1. So this implies that H min of T is bigger than some C4 divided by 2 T max. Oops, I forgot the square root here, right? Because this, I forgot to take the square root. Okay. Since H min divided by H max. Now, to get the other inequality, I can estimate ddt of H min. The minimum, the Laplacian is greater or equal to 0, so I can again throw away the Laplacian. So I have here now H times A squared at the point where the minimum is attained, but A squared is bigger than 1 on n H squared. It's always the case. Used this already a lot. This is 1 on n H min cubed. Okay. And which means that I get ddt of H min squared greater or equal H min to the minus 2 is then less or equal to minus 2 on n times H min to the minus 4. No, not minus 4. This cancels out, right? This gives a minus 4 multiplied by H min to the 4. So we get just minus 2 on n. And then arguing SB4, since H min also goes, because of this property, H min also goes to infinity, we can use the same argument as before to now conclude the upper bound for H min of T. This must be bounded by by 1 over, by square root of n divided by square root of T max minus T. Same argument as before, except for the factor n. But this implies, since H max is bounded by some multiple times H min, because the ratio goes to 1, this implies that H max of T must be bounded by some other constant C5 divided by maybe twice this and now we have the both the lower bound on the mean curvature and the upper bound with the same 1 over square root of the remaining time, which establishes the proposition. Okay, now we know exactly what the blow-up rate is, and this now enables us to rescale things. And now for the rescaling, we have 3 possibilities. We want to show that after rescaling, the surfaces converge to the round sphere. So rescaling procedures. And there's three possibilities. There's the first probability, in some sense, is the simplest one that is just suggested by this particular rescaling rate. So let's make first an observation. Since the surfaces M and T are convex, they move in one direction enclosing convex domains omega t, boundary omega t is the MNT, containing each other. Okay. Now, since the diameter goes to 0, we have just seen, since the diameter MNT is less than the constant times H max of T, which tends to 0, this must mean, since these domains are shrinking, the diameter is going to 0, that the MNT must converge to some point. MNT converge to some point y infinity in Rn plus 1 as t approaches c. So we have already proven that the surfaces approach some point in the ambient space. Now, when we do the rescaling, of course, we should do the rescaling from this point, y infinity. So the first way to rescale is to simply set rescale by the blow-up rate. Simply set f tilde of pt is equal to 1 over 2 times T max minus T times F minus y infinity. Now, with this rescaling, first of all, notice that the surfaces cannot disappear at infinity. Note that then ddt, the speed of f tilde, is ddt, no, the speed of f is less than the mean curvature, because ddt of f is the mean curvature vector. So by our estimate on H max, our blow-up rate, this is bounded by a constant divided by the remaining time. But this, if you integrate this, you get that f of pt minus f at t max, which is y infinity, is less than integrating this from somewhere to Tmax, but this integrated gives you square root of Tmax minus T. So you get some square root of Tmax minus T, which means that this is bound. So F tilde PT is uniformly bounded by C. So the surfaces with this rescaling cannot disappear. On the other hand, the rescaling is such that now the mean curvature is bounded above and below, because we have rescaled exactly with the rate of the mean curvature. So also the mean curvature is uniformly bounded now after rescaling between C3 and C3 minus, bigger than 0, because of our previous by proposition. On the other hand, the second fundamental form is by convexity bounded by h squared. So this is also bounded by C3 squared. So we have bounded curvature. Now, once we have the curvature bounded, you can proceed just like in the short time existence proof, where we showed that if the curvature is bounded, you can bound all higher derivatives in order to extend the flow. So you can now also show that all higher derivative of curvature satisfy the appropriate blow-up rates with higher powers. So from there, you get that, say, gradient n of A tilde is less than some constant depending on m divided by Tmax minus T to the appropriate power n plus 1/2. Actually, this is without the tilde. And then after rescaling, it means that gradient m A tilde is bounded by Cn. So by Arcela-Ascoli, you get convergence to some smooth hypersurface. Convergence of subsequences to smooth and tilde infinity, but let's see what that could be. Use our pinching estimate. The trace-free part of the second fundamental form divided by the mean curvature of the rescaled surfaces. Because it's scaling invariant, this is the same as the trace-free part of the original surfaces. Right? This is the scaling invariance. And this had the estimate C0 times h to the minus sigma, which tends to 0 uniformly, because we know that the minimum of the mean curvature also goes to 0. So this thing goes uniformly to 0, and h tilde is bounded from below. So this must mean in the limit, A0 must be infinite, must be 0. A0 is identically 0 on m tilde infinity. And this must mean m tilde infinity is a sphere. So you get convergence to a sphere of any subsequence. This is not yet perfectly beautiful because with a little bit more work, you can actually show it converges nicely, but that requires some extra estimate, which I don't want to do now, because in this rescaling method, this would be very special to the convex case. So let's rather focus on the other rescaling methods. Now, the second rescaling method, and by the way, this is very much analogous to the kind of rescalings that we do in Ricci flow. There's sort of, in my other course that I've put online at the MFO on Ricci flow, there is a lecture where this analogous scaling procedure is explained for the Ricci flow. So the second possibility to rescale, which is again special to the convex case, would be to rescale to keep the area of the surface constant. So rescale to achieve that the area is constant. Well, this means we take our f tilde of pt to be a factor which we not determined, like we just did here, which we took the blow-up rate. Now we say we choose this factor times the original surface minus its limit point, such that integral d mu tilde over mn is identically the area of the initial surface. Now, well, since the area of the rescaled surface is obviously psi to the n times the surface of the real flow, we get that 0 is ddt of integral d mu tilde mn. This is our requirement. The area doesn't change. So we get n times psi to the n minus 1 times psi dash times integral d mu, plus the evolution of the area here, which we know is minus psi to the n times integral of the mean curvature squared. That was the evolution equation of the area under the original mean curvature flow. So for our requirement to be true, it must be true that we can write that we get that psi dash over psi is equal to 1 over n times little h, where little h is the mean value of the mean curvature squared. Okay. So we get an ODE of psi dash. And now it turns out if you do such a rescaling, you should also rescale the time variable. And if we rescale time by setting t tilde of t to be the integral from 0 to t of psi squared of tau d tau, such that the t tilde with respect to dt is equal to psi squared, then you can compute an evolution equation of f tilde with respect to t tilde. This is d f tilde with respect to dt times dt dt tilde. So this is equal to, of course, I've also just psi to the -2 times the evolution here, and this is psi dash times f of pt minus y infinity. And then the other term we get is plus psi of t times ddtf, which is the mean curvature vector. Now, psi to the -1 times psi is psi to the -1 times the mean curvature. So this is exactly the mean curvature vector of the tilde metric. So that was the reason to choose this change of time coordinate. And the extra term now comes in if I use this evolution equation for psi dash. Here I get a extra term which represents the and this turns out to be exactly this. So you get sort of an extra term pushing out from the center y infinity, sort of rescaling from the point where it contracts to. And now, with a little bit of extra work, which I don't want to carry out, you can now use the, since this h tilde, this extra term is just a constant for each time, the evolution equations for this new evolution equation don't change much with respect to the old one. So you can show that if P satisfies ddtp equals Laplace P plus some Q, this is a typical way you get evolution equation for some quantity, and the degree of P is alpha, then if you form the corresponding P-scaled quantity P tilde and use the evolution equation with respect to the T tilde time parameter, you get the old evolution equation back plus an extra term, which is exactly, now I have to look, which is equal to alpha over n times h tilde times p tilde. So you get sort of this extra term coming, and of course in the case here, this would be the case where alpha is equal to 1, and you have an extra term 1 over n h tilde f tilde. But for the mean curvature, for example, this would mean a negative term. You get a negative term here, which is a good term. And similarly for the gradient of mean curvature term. And now if you use the old estimates, with a little bit of extra work, you can get, this might be a good exercise to go through this old paper of mine, how to do this. You get that the gradient h tilde can be estimated by some exponential decay with respect to the t tilde variable. And you can, and this of course also means that the mean curvature approaches its mean value exponentially fast because you have the diameter bounded after rescaling. So here in this setting, you actually get exponential convergence. Around here, just like in the first rescaling of area Mn0. So in some sense, this result is more beautiful, but you have to work harder because you have to go through your old estimates again. It's not very hard. You can use all the tricks from before. You just have to add this extra term and see what it does. And for the curvature terms, of course, it helps you because then the alpha is negative and you get this good term and that leads to the exponential decay. Okay, but again, this is very special. In general, this will not work, this method. So, for example, if you were to try to so remark, this doesn't work without convexity. And the corresponding beautiful estimates that we have, if you were to do this in a situation like this, and you rescale with the average of the mean curvature, then this would still go, so you keep the area constant, but then you get a single, this would still, after rescaling, the rescaling would simply not be enough. You would end up with a situation like this, where you have something bad is still happening here. The area is finite, but you still have a singularity, and there is no way to analyze. You're just as clever as you were before. The extra term coming from here is simply not strong enough to resolve the singularity and make it into something that you can recognize. So this method here only works in the nice way where everything in the end contracts to one point, and then sort of the uniform rescaling gives you a round sphere. So both methods of rescaling are somewhat restricted. So the most powerful way to rescale the singularity is the following one, because it can be generalized to many other situations. And the idea is to rescale in such a way that mean curvature flow remains mean curvature flow. So parabolic rescaling inside the class of mean curvature flows. It's the third possibility. And for this, suppose MNT is solution of the curvature flow on some time interval Tmax up to Tmax finite, say. And then we know the curvature is going to infinity. Pi and Mn is a sequence of points. I times and lambda I greater than 0 scale. So there are a sequence of points, a sequence of times. Let's assume the times approach Tmax. And let's assume the lambda i's are going to go to infinity. They are all positive. But let's not make, otherwise we don't have to make much assumptions for the initial setup. And then we will see what we're going to do. And then simply set Fi p and tau. So you introduce again a new time variable, and then you rescale the whole thing by a huge factor, lambda I. Think of lambda I as a number going to infinity, times, and then you take the original f at the point p, and now you rescale time, and now you rescale the original f with lambda I, then you have to rescale the original time t with lambda I squared, meaning you rescale the parameter tau with lambda I to the -2. And then we shift it a bit so that at tau equals 0, we have the old time ti. So we do a shift in time. And then we can do a shift in space to put the point pi at time ti into the at time 0. So at time tau equals 0, this will be the origin. So we put the point pi at time ti, we shift it in our rescaling to the origin. So this is now obviously defined on a new time interval where tau is less than, now this was running up to t max, because t was running up to t max. If this runs up to t max, then tau runs up to lambda I squared times t max minus ti. And if this started at time 0, then this parameter tau can start at time minus lambda I squared ti. And note that the left-hand bound, if lambda I tends to infinity and ti tends to t max, which is some positive number, then this clearly tends to minus infinity. So we get really a rescaled picture where the left-hand time interval is pushed back to minus infinity. And already I said that this shift in space and time means that fi at pi 0 is equal to, if I put in 0 here, this cancels out, so this is 0. So I've shifted these points to 0. So this is a general way of rescaling. And now we have to see what we do in our particular situation. Now, in our particular situation, we just take any sequence of points. In fact, we can fix pi because we know this guy converges to y infinity. We could have just subtracted y infinity. So in our case, can take any sequence ti tending to t max, can take any sequence pi in infinity, noting that f of pi ti converges to y infinity. We already know that. But the lambda I, we have to choose in a clever way. Now the lambda I is the way you rescale. Now we want to rescale in such a way that we see something. So we rescale by the curvature in order to make the curvature bounded. So choosing lambda I is crucial. Here we choose lambda I to be the maximum of the curvature at the maximum, yeah, we could take just the maximum of the mean curvature, on the interval from 0 to Ti cross Mn. Then, because the mean curvature scales, the mean curvature scales exactly the other way around. So then this is equal to H max times at Ti times lambda I to the minus 1 satisfies H tilde max is less than 1 on minus lambda I squared Ti up to lambda I squared T max minus Ti. Also, we now know that the right-hand side of this time interval also we get lambda I squared times T max minus Ti. This is equal to H max squared at T is less than if we take Ti such that the maximum is attained at Ti, so we get that this is equal to H max at Ti squared times T max minus Ti. If, yeah, well, it's certainly greater than that. And this is, we know that this is greater than some constant, greater than 0. Okay, so this is certainly, and on the other hand, this is also bounded from above by our other estimate that the mean curvature is equivalent to this difference. So we get that this time interval here converges, so this time interval here converges to a time interval which looks like minus infinity tau tau max, where tau max is between 0 and infinity. Okay, this is what we get from there, and oops, sorry, this is not right. This is only up to time Ti, which is the time when tau is 0. So the bound we get here, but this converges. But the whole time, sorry, I made a mess of this. So we get a uniform bound mean curvature less than 1 up to time 0, but we get a smooth solution bound which may be larger than this, get a smooth solution as I under I tends to infinity on minus infinity, and then we get this tau max. And this tau max is between 0 and infinity. Now, why do we get a smooth solution? Well, because h tilde is bounded by 1, and on each compact time interval here, it is bounded by some other constant. And our solutions, most important thing, which I forgot to say so far, is the most important thing is all our solutions ddt fi p tau, dd tau fi of p tau. By the way, we have set it up. It's the formula. There's no ddt from here, so forget this term. So we just have to differentiate this one. And then we get from here the mean curvature vector multiplied at the original f, multiplied with lambda I to the minus 2 times lambda I is the mean curvature vector multiplied with lambda I to the minus 1. But that is exactly the mean curvature vector of the fi metric. So we get a solution of mean curvature flow again. And notice that because of convexity, we have the AIs are bounded by the HI, and these are uniformly bounded on each compact subinterval of this interval I. So we have uniform bounds on all the second fundamental forms by convexity because you have uniform bounds on the mean curvature. And now, because it's a solution of mean curvature flow, we know that this implies uniform bounds on all higher derivatives. So you have uniform bounds on all higher derivatives on each compact subset of this time interval. But that must mean that by Arcela-Ascoli, as I tends to infinity, you don't just get a sequence, a subsequence converging in terms of the surfaces, you get the whole flow converging to a limit mean curvature flow on this long time interval. So this parabolic rescaling, okay, yeah, let's be slow. So we get higher derivative estimates on each compact subset of I. Then Arcela-Ascoli. Arcela-Ascoli. As lambda I is to infinity, get a subsequence of flows converging to a mean curvature flow f tilde infinity, and corresponding to surfaces m and tilde infinity. And now, as we've seen before, it must, as before, in 1 and 2, the trace-free part of the second fundamental form must again be 0 on these guys because of our pinching estimate. So a 0 infinity is identically 0. So this must be a sequence of concentric spheres shrinking. So m infinity tau is shrinking concentric spheres. So we have sort of this picture of mean curvature flow on the finite time interval contracting to this point. And now we scale the whole flow. And then the whole flow eventually converges to the flow of concentric spheres starting at time minus infinity and converging to a point in finite time, tau max, to the point y infinity. And that is a nicer picture because in this way, we really have taken a parabolic limit, not just the limit of individual surfaces. And we have rescaled the whole mean curvature flow. That's sometimes called tangent flow. So the formulation of this result would be each tangent flow is just a flow of round spheres around the point y infinity. And that gives a complete description of the singularities. And this is much more flexible situation because now I can sort of, in this situation, carefully choose my points, approaching the interesting point here, and I can adjust the scale lambda I to what is happening here rather than to the area of the whole surface. So this last method is much more flexible, and we see how this can be applied in other situations in future lectures. Thank you.